This is the second lesson in nuclear decay. See the description of this video. There are all the necessary and the useful links related to my other lessons are given. Also, if you subscribe my channel, you will get notifications when I upload new videos. Okay, in my first lesson, I discussed mainly about binding energy and binding energy per nucleon and how the stability of the nucleus is decided by one of the factors is binding energy and the binding energy per nucleon. There are many other factors also decide the stability of the nucleus, such as proton to neutron ratio, the deformation of the nucleus. Like that, there are many different factors. None of them are in your syllabus. Mainly they are all related to nuclear physics. Okay, so in this lesson, I am going to discuss about radioactivity or radioactive decay. So in my first lesson, I told there could be two different types of nuclear decay. The first one is natural decay, or we call the natural decay as a spontaneous decay. Spontaneous decay means it happens in its own without any external interference. The example for spontaneous decay is radioactive decay. The second method or second thing is artificial transmutation. There human intervention required. Say for example, a nucleus should be bombarded by a particle such as proton or neutron or alpha particle, or even when a nucleus is bombarded by using a photon, there will be change in the structure of the nucleus. So there will be new elements could be formed. That is the artificial transmutation. Good example for artificial transmutation, I told that in the first lesson, nuclear fission, nuclear fusion, and there are many other examples I discussed in the first lesson. Okay, so in my third lesson, I'll discuss about artificial transmutations, including fission and fusion. So in this lesson, I'm going to discuss radioactivity or radioactive decay. Okay, so what during radioactive decay, an unstable nucleus becomes a stable nucleus by emitting one of the three particles. That means it could emit either alpha or beta minus or beta plus. Additionally, it could emit gamma radiation also. So which factor decides the emission of the type of particle? Actually, it's mainly decided by the number of protons and neutrons. If the total number of protons and neutrons together is very large, very high, then that nucleus will emit mainly, or it could emit mostly alpha particle. For example, you can see which nuclei are emitting alpha particles. You can see mostly heavy nucleus. Mostly the heavy nucleus emit alpha particles, such as polonium, the mass number 210, that emits alpha particle. When it emits alpha particle, it becomes lead, right? Same way thorium, its mass number 228. So when thorium emits alpha particle, it becomes radium. Same way we can say radon 222. So that also emits alpha particle and it becomes polonium. Or maybe even radium 228, yeah, mass number, I'm right, I think. Radium 228, when it emits alpha particle, it becomes radon. So like that, if the mass number is very large, 210, 228, 222, so there what happens, protons and neutrons together form a cluster inside the parent nucleus. We call, you learned that in IGCSE, the initial nucleus is called parent nucleus. So inside the parent nucleus, they form a cluster where two protons and two neutrons join together and escape. That happens in alpha decay. And you can see where the beta decay occurs. You can see if the number of protons is reasonably larger than number of neutrons. Generally, I'm saying the general trend. If the number of protons is larger than number of neutrons, then there the proton will break up. So there it will emit positron or beta plus. If the number of neutron is larger than number of proton, there it emits beta minus, the electron will be emitted. Okay, so this is the general concept. I'm not saying 100% this is accurate, but this is the general trend that decides the emission of type of particle. So normal students ask how to decide, but anyway, it mainly depends on nuclear physics. I told in my first lesson, actually what we are learning as a nuclear decay is a small portion or small topic in the vast topic in modern physics called nuclear physics. So there are a lot of theories related to nuclear decay, but we don't deal anything of them in A-level syllabus. Okay, so we know that, so first I'll start with alpha decay. So I already told that if the number of protons and neutrons both form a massive nucleon number or massive mass number, that element will become unstable, because when there are a lot of protons, there will be repulsive force among them due to electrostatic force inside the nucleus. So it will try to balance it. So there are two protons and two neutrons will form a cluster inside it, and they escape out of the nucleus. The thrown two protons and two neutrons together is actually the helium nucleus, and that is called the alpha particle. You learn all these things in IGCSE also. So the general equation, the decay equation for alpha particle decay is given by like this. XAZ, so A is the mass number, Z is the atomic number for nucleus, we say that. So, or we can say A is the mass number, or we can call it as baryon number. We deal with nucleus. So, if I say X is the name of the element, then A is the baryon number, Z is the charge. That way also we can say, you know, the charge of the nucleus is exactly equal to charge of the proton. Either way we can consider. So XAZ will become Y, that's the daughter nucleus, and it becomes alpha particle, that is the helium nucleus. We can denote alpha, or we can denote it as He2 plus. Either way we can write the alpha particle. So helium nucleus is the alpha. You learn that all in IGCSE. So alpha 4, 4 is the mass number or baryon number, 2 is the charge, because He2 plus. So I told that in I told that in the first lesson, during this all type of nuclear decay, the certain factors what we learn in unit 4 particle physics, all factors must be conserved. One of it is baryon number must be conserved, charge must be conserved. So the baryon number must be conserved means A, this is 4 means it should be A minus 4. Z, this 2 means Z minus 2. Also we know that X is called the parent nucleus, Y is called daughter nucleus, this is alpha particle, both together is called decay product. Okay, that's the way we call them. Okay, so O-level IGCSE you learned that there are two different types of beta decay. One is called beta minus, other one is called beta plus. Beta minus is the electron, just normal electron, and beta plus is the positron, antiparticle of electron or antimatter of electron. So in which situation normally the nucleus emits beta minus means if the number of neutrons is more than number of protons, then what happens? A neutron will break up and form a proton. So there the reaction I can say, I can write like this, the fundamental reaction I can say, the neutron N10, that's a notation, it breaks up or decays into proton 1,1 and it emits electron E minus 0 minus 1. This is the beta particle. So when they found first time, they didn't know it is beta, so they didn't know it is electron, so they called it as beta, but we know that it's an electron. Okay, so and also, you know, to balance, I told that all these decays should obey the conservation properties. So here you can see baryon number is balanced, neutron is a baryon, proton is a baryon number is balanced, electron is a lepton. So baryon number is balanced, you can see the charge is balanced, baryon number balanced, charge is balanced. So the next factor, the lepton number should be balanced. So the lepton number should be balanced means we know that if I think about the lepton number, neutron is a baryon, It has no lepton number 0. Proton is a baryon, lepton number 0, but electron is a lepton, it should have +1. So that means we should have a particle that should have a lepton number -1 and no charge, no baryon number. So the only particle is anti-electron neutrino. Okay, so that's anti-electron neutrino. Its lepton number is -1. Now lepton number also balanced. Okay, so this is the emission of fundamental what happens inside the nucleus. So this is the way we can write the beta minus decay. But when we write in terms of the name of an element, the nucleus, I can say XAZ, that's the parent nucleus. It becomes Y. We should balance it. So E minus 0 minus 1 plus anti-electron neutrino. So we should balance it. So -1, 0 means it should be Z plus 1. So there will be increase in charge or increase in atomic number. The baryon number or the mass number has no change. So the mass number remains unchanged. So that very important. Later I'll discuss about energy release. I need this. There's no change in mass number when we consider emission of beta minus. Same way when I consider emission of beta plus, when it happens, the emission of positron happens when the number of protons more than number of neutrons. Proton breaks up into neutron and throw away the positron. So therefore beta plus, a proton E11 breaks up into a neutron 10, and it's the positron, sorry, that's a positron E plus 0 plus 1. Here also the lepton number should be balanced. You know positron is an anti-lepton, lepton number -1, so we should have a lepton number +1, a particle with lepton number +1 that without any charge. So the only possibility is neutrino. So here now everything is balanced. Baryon number balanced, charge is balanced, and also lepton number balanced. Okay, so this is the positron called beta plus. When I write the same reaction equation in terms of nucleus notation, XAZ, that's a parent nucleus. It becomes the daughter nucleus Y, E plus 0 plus 1 or beta plus. This also I can write either beta minus 0 minus 1. So this could be written as beta plus 0 plus 1. Anyway, either way we can write. So neutrino 0 0. So when we balance it, here that should be Z minus 1A. So here also you can see there is a change in the charge or change in the atomic number, no change in mass number or no change in baryon number. Okay, so the next thing is gamma radiation. Okay, why does a nucleus emits gamma radiation? It emits, in my first lesson I told that there are different models I use to explain the structure of the nucleus. There are different mathematical models, liquid drop model, quantum mechanical tunneling model, like that. There are different models. There are around 10 different models are used to explain the structure of the nucleus, and different models explain different aspects of the nucleus also. Anyway, according to one of the models says that, I told that in the unit 1 also, one of the models says that inside the nucleus, the nucleons are arranged. The protons and neutrons are arranged in different energy levels, like what we learned in unit 2 in spectra. There we learned that electrons are at different energy levels or different shells around the nucleus. Like that, inside the nucleus, nucleons are arranged or kept in different energy levels. So whenever a nucleus decays, it could be alpha decay or beta plus or beta minus or even artificial transmutation, whatever happens. Whenever a nucleus decays, the existing nucleons, after throwing away certain elements, the existing nucleons will be rearranged themselves such that to get the most stable configuration. So during that rearrangement, certain nucleons could be excited to high energy level. So that is unstable. So they will, when they come back to the low energy level, the surplus energy or the excess energy will be released in the form of gamma radiation. So in A level, we don't need all these nuclear potential energy, those things. So in case if they ask like what's the reason for emission of gamma radiation, simply you can say after emission of alpha or beta minus or beta plus particle, the nucleus could be excited to higher energy level. So the surplus energy will be emitted in the form of gamma radiation when the nucleus return to the lowest energy level. That is enough for A level. So mostly the gamma radiation will be emitted after emission of alpha or beta plus or beta minus particle. Okay, so the next thing is about, it's a very common question students ask, can a particular type of nucleus emit two different types of particles? No, it can't. Say for example, if it is radium, it emits only alpha. Radium, it emits only alpha. I told that earlier when I start this lesson. If it is like a thorium isotope 228, it emits also only alpha. If it is like a cobalt 60, cobalt is a radioactive element, cobalt 60, it becomes nickel by emitting beta minus. So like that, one particular type of nucleus can emit only one type of particle. But when we have a radioactive sample and when we do test by using Geiger-Müller counter, O-level, you heard about it. When we try to find out the particles the given sample emitting, it could emit sometimes all three particles like alpha particle, beta minus and gamma photons. How is it possible, students, they ask. So the reason, when you are given a sample, radioactive sample, this is the radioactive sample, maybe this is radium. Initially, imagine it's a pure radium. So when the radium decays, the given sample, right? When the radium decays, it will form radon by emitting alpha particle. Now inside the given sample, both radium and radon are there. Something like that, if I write in a very general format, you are given a radioactive nucleus X in the form of sample, radioactive sample, X is given to you. So that might emit alpha particle and becomes Y. Now the daughter nucleus Y also still unstable. So it will try to become more stable nucleus. So the given sample, this is the given sample, it consists initially purely only X, but after certain time later, it will consist of both X and Y. So Y is also, in case if Y is also an unstable nucleus, then what will happen? Y will decay maybe by emitting beta minus. So Y will decay and become Z by emitting beta minus. So the given sample will consist of both X, Y and Z. So X is emitting alpha, Y is emitting beta minus. Maybe after emission of one of these, it could emit gamma also. So when you use GM counter, Geiger-Müller counter, to check what type of particle is it emitting, you might detect all the three particles. But remember that one particular nucleus, one type of nucleus won't emit both alpha and beta minus. Okay, so one particular type of nucleus will emit one type of particle, either alpha or beta. After emission of alpha beta, when the daughter nucleus goes to excited state, yes, it can emit gamma, but one particular type of nucleus won't emit both alpha and beta. Okay, so actually beta is emitted by the daughter nucleus. The daughter nucleus also inside the given sample. So when we check for the emitted particles, we might get a result. The given sample is emitting all three, right? That's the reason for the confusion. Okay, so next about range of a particle. Generally we say alpha particle, beta and gamma, they all are ionizing particles. That means when they travel through a medium such as air or liquid or even through paper, whatever it is, when they travel through a medium, they will collide with the atoms or electrons in the medium, and they will ionize the atoms in the medium. So during this ionization, what happens? The particles, whether alpha or beta or gamma, when they travel through the medium due to collision, they will lose their kinetic energy, but not the beta plus, because whenever beta plus meets an electron, there will be annihilation. We learned that in unit 4. So you can see my unit 4 lessons there I discuss about annihilation. So I'm talking about alpha, beta minus and gamma photons here. Okay, so when they travel through a medium, they ionize the medium. During the ionization, they hit the electrons of the atoms of the medium, so these particles will lose their kinetic energy. Since alpha particle has the largest dimension, largest size, it travels slowly, so when it since it has larger size, it has more chance of hitting the electrons of the atoms in the medium. So alpha particle produces several collisions, or rate of collision of alpha particle in a medium is the highest. Therefore, alpha particle will lose its kinetic energy when it travels through very short distance, and it will be stopped. When it loses its kinetic energy, it won't be able to travel further. So generally we say alpha particle, it can travel almost 8 centimeter. Different books give slightly different depending on the energy of the alpha particle emitted from the parent nucleus, but generally 5 centimeter to 8 centimeter through air. That's the maximum distance alpha particle can travel through air. Alpha particle can be easily stopped by a thin sheet of paper. So it can't travel even through paper. So students normally ask why it travels through air around 5 centimeter, but through paper it couldn't travel even through a thin sheet of paper. The reason, thin sheet of paper, the density of paper is more than density of air. So density of paper more means when you think about the thickness, there it will need several atoms compared to when it traveled through air. So when it meets several atoms in the thickness of paper, when it travels through the paper, so it will lose its kinetic energy completely, and it's unable to penetrate through the paper. So the density increases also, the number of collisions increases within in a given thickness, because the number of layers of the atoms in the medium increases. So remember that alpha particle can travel just 5 centimeter to 8 centimeter through air. It could be completely stopped by a thin sheet of paper. Beta minus particle that can travel almost 30 centimeter through air. It can mostly, very low energy beta particle cannot travel through paper, but anyway, generally the moderate energy or high energy beta can very well pass through thin sheet of paper, but it could be completely stopped by few millimeter thickness of aluminium sheet. So few millimeter thickness means I can say around 5 millimeter, 5 millimeter thickness of aluminium can completely stop all the beta minus particles. Beta plus we don't talk because it undergoes annihilation. Same way, gamma radiation, it can very well pass through air, it can very well pass through sheet of paper. Same way, it can very well pass through aluminium. It could be stopped by few centimeter thickness of lead. You know, lead has the highest density, so higher density compared to aluminium. So gamma photons will be stopped by few centimeter thickness of lead. So remember these absorbers, we call them as absorbers in practicals. So for alpha particle, we use normally thin sheet of paper as the absorber. For beta minus, we use few millimeter thickness of aluminium sheet, and for gamma, few centimeter thickness of lead. So these are the medium used as absorbers when we are detecting these particles from a radioactive sample. Even this type of questions came in IGCSE paper. So normally when we are doing practical, first we should think about the background radiation that also you learn in IGCSE. Background radiation means the radiation emitted from the environment, such as rocks, radiation from the sun, or maybe even we know that certain gases, they are the elements that emits radiation, and that's the reason for the background radiation. So normally we use Geiger-Müller counter, Geiger-Müller tube with counter to measure the radiation. So whenever we do practical, first we should measure the background count rate. How do we measure the background count rate? We should keep all the radioactive elements in the laboratory in a lead shielded container and switch on the Geiger-Müller tube and the counter for around 20 minutes. Record the total count, divide it by total time in second, you will get the count rate. So repeat this practical 5 times and find the average value that will give the background count rate. Okay, so if you are given an unknown radioactive sample X, how can you experimentally confirm what type of particle is it emitting? Okay, how to identify the type of particles the unknown radioactive sample emitting? So first we normally say these are the steps. Remember, O-level questions paper also this type of questions appeared. First we should measure the background count rate. Then keep the sample, given sample, closer to the GM tube window and measure the count rate. Okay, first measure the background count rate. Keep the source closer to the GM tube window and measure the count rate. Now keep a thin sheet of paper between the sample and the Geiger-Müller tube window. When you keep a thin sheet of paper, if there is no significant drop in the count rate, that means the sample is not emitting alpha. If there is a significant drop in the count rate, that means paper is blocking certain particles, but paper can block only alpha. So the given sample is emitting alpha particle. Understand? So that's the way we check for alpha particles. Measure the background count rate. Keep the source closer to the source, given source closer to the GM tube window. Measure the count rate. Keep a thin sheet of paper between the source and the GM tube window and measure the count rate. If there is no significant drop in the count rate, that means the given sample is not emitting alpha. If there is significant drop in the count rate, the given sample is emitting alpha. Okay, then how to check whether a given sample is emitting beta minus? Okay, again for beta minus, now I am going to tell how to check a sample is emitting beta minus. Measure the background count rate, keep the source closer to the GM tube window and keep a thin sheet of paper. So both have to be kept. So if this is the GM tube window, this is the GM tube, this is the given sample. First measure the background count rate, it's connected to the GM counter. First measure the background count rate without sample, sample X, whatever it is. Now keep a thin sheet of paper. I am checking for beta minus, whether the sample is emitting beta minus, that's my aim. So keep the source closer to the GM tube window and keep a thin sheet of paper. And now check the count rate. If the count rate is well above the background count rate, that means certain particles or radiation passing through the paper. So alpha is blocked by the paper. So the count rate what you are getting, which is well above the background count rate, could be only due to beta minus or only due to gamma or both together. Either 3 possibilities: only due to beta minus or only due to gamma, because you already blocked the alpha by using paper. So the count rate what you are getting is only due to beta minus or only due to gamma. So maybe it would have emitted alpha and gamma, means alpha is blocked, gamma is passing through the paper. We don't know what is it. Or maybe both are passing through the paper. Right? So I want to check for beta minus. Okay, after keeping the paper, now the count rate is well above the background count rate. Now by keeping the paper, no problem, by keeping the paper, keep a thin sheet of a few millimeter thickness of aluminium sheet. By keeping the paper, you can keep few millimeter thickness of aluminium sheet between the source and the GM tube window. Now when you keep an aluminium sheet, if there is significant drop in the count rate, means there is beta minus. If there is no change in the count rate, there is no beta minus, means the radiation which is passing through aluminium as well as paper is mostly gamma. Understand? So that's the way we check for beta minus. So again I am telling, keep the source closer to the GM tube window. First keep a thin sheet of paper. This is a GM tube window. Keep the source closer to the GM tube window and keep a thin sheet of paper and measure the count rate. If the count rate is well above the background count rate, it could be due to either beta minus or gamma or both together. Right. Now keep few millimeter thickness of aluminium sheet. This is the aluminium sheet. Now you are keeping it. So when you keep the aluminium sheet, if the count rate shows a significant drop, that means there is beta minus. If there is no change in the count rate, that means there is no beta minus. Okay, so next, how to confirm a sample is emitting gamma radiation. So that is very simple. Same way, complete the setup like this. Geiger-Müller tube connected to the Geiger-Müller counter. Keep the given sample. So I already told you how to detect alpha and beta minus. To confirm whether it's emitting, the given sample is emitting gamma radiation. So directly keep few millimeter thickness of aluminium sheet. So first you should measure the background count rate. Then keep the aluminium sheet between the sample and the Geiger-Müller window, Geiger-Müller GM tube window, and measure the count rate. So if the count rate is still above the background count rate, the only particle, the radioactive particle that can pass through the aluminium sheet is gamma. But to confirm whether it is gamma radiation, now keep few centimeter thickness of lead in the region between the sample and the GM tube. If the count rate drops to background count rate, that means there is gamma. Okay, so this is the way we detect the type of particles emitted from a sample by using Geiger-Müller counter and the Geiger-Müller tube. Okay, so how can we confirm a given sample is emitting only alpha? So this type of questions also sometimes comes. How to confirm a given sample is emitting only alpha? So it's not emitting gamma, and also it's emitting only alpha means you know, a sample may be X is the radioactive element, X is the radioactive element. So that's a parent nucleus, becomes Y the daughter nucleus, and alpha. So if it is emitting only alpha means, you know, I already told that the given sample will consist of initially only X, but later there will be both X and Y, because when the nucleus decays, X decays, it will produce Y. But if Y is a stable nucleus, it won't decay further. Or maybe Y might have a very large half-life. I'm going to introduce half-life, means the average time taken for it to decay to the half of the initial value. But anyway, if it is comparatively, if it is very stable, it will emit only alpha. It looks like emitting only alpha. So how can we confirm a given sample is emitting only alpha? Okay, simple practical. The same setup. So again I am drawing it, the same setup. This is the Geiger-Müller tube connected to the GM counter. First measure the background count rate. Then keep the given sample X closer to the GM tube window. Measure the count rate. It will be much above the background count rate. Then keep a thin sheet of paper. Keep a thin sheet of paper and measure the count rate again. When you measure the count rate again, if the count rate drops to background count rate, that word should be there. If the count rate drops to background count rate, the paper is blocking all the particles. That means no particle is passing through the paper. That means the given sample is emitting only alpha. Okay, right. Then how to confirm it's emitting only beta? Beta means beta minus, only beta. How to experimentally confirm that? Okay, so to confirm it's emitting only beta. How to confirm experimentally? Measure the background count rate. Keep the source closer to the GM tube window and measure the count rate. Then keep a thin sheet of paper. Keep a thin sheet of paper. When you keep a thin sheet of paper, if there is no significant drop in the count rate, means the sample is not emitting alpha. Okay, again measure the background count rate. Keep the source closer to the GM tube window. Measure the count rate. Now keep a thin sheet of paper between the source and the sample. When you keep a thin sheet of paper, if there is no significant drop in the count rate, means the sample is not emitting alpha. Because if it is emitting alpha, it will be blocked by the paper, so there will be a drop in the count rate. So no drop in the count rate means the sample is not emitting alpha. So still the count rate is same as earlier. So it could be either beta minus or gamma. Now keep a thin sheet of a few millimeter thickness of aluminium. So a few millimeter thickness of aluminium sheet, now keep it. When you keep the aluminium sheet, if the count rate drops to background count rate, that means we know it's not emitting alpha, already we confirm it. Now when you keep a thin sheet of aluminium, if the count rate drops to background count rate, means aluminium is blocking everything. So if there is gamma, it would have penetrated through the aluminium sheet and the count rate won't drop to background count rate, but the count rate is dropping to background count rate. So if the count rate drops to background count rate, it is emitting only beta minus. So again I'll tell that. Measure the background count rate. Keep the source closer to the GM tube window and measure the count rate. Keep a thin sheet of paper and measure the count rate. If there is no significant drop in the count rate, there is no alpha. Then keep an aluminium sheet and measure the count rate. If the count rate drops to background count rate, there is only beta minus. Okay, next thing is about alpha and gamma. No beta. So the given sample is not emitting beta. So the given radioactive sample X is emitting only alpha and gamma. How to confirm that practically? Measure the background count rate. Keep the source closer to the GM tube window. Measure the count rate. When you keep a thin sheet of paper and measure the count rate again, there will be significant drop in the count rate. Significant drop in the count rate, but still well above the background count rate. Significant drop in the count rate, still well above the background count rate, means there is alpha. Paper is blocking alpha. So there will be significant drop in the count rate, but well above the background count rate, means there is alpha. Now by keeping the paper, now keep a thin sheet of aluminium, few millimeter thickness of aluminium. When you keep few millimeter thickness of aluminium, there is no change in the count rate. There is no significant change in the count rate, means no beta minus. Still the count rate is well above the background count rate as earlier. So most probably gamma. To confirm it, you can remove the paper and the aluminium sheet and keep few centimeter thickness of lead. Now keep a lead and measure the count rate. If the count rate drops to background count rate, there is gamma. So there is gamma. Okay, so that's the way we check whether it's emitting only alpha and gamma, no beta minus. Okay, so the next topic is activity. What is activity? Rate of disintegration or number of nuclei decay per second is called activity. So activity and count rate, are they same in numerical values? It depends. Say for example, if the given sample X as a parent nucleus becomes Y by emitting alpha particle. I take an example for alpha particle. So X is the given sample. So when you have the element X, and if Y becomes a stable nucleus, then the activity, in 1 second, how many X nuclei are decayed? During each decay, they emit only one alpha. So the count rate theoretically, but depending on the dead time of the Geiger-Müller counter, the count rate can vary. But anyway, theoretically, I can say there are number of decay per second and the number of count rate of alpha will be the same if Y is a stable nucleus. So if the daughter nucleus is a stable nucleus, theoretically the activity means number of decay per second, rate of disintegration, and the count rate, number of alpha or number of beta counted per second will be the same. But if Y, the daughter nucleus, is also unstable, maybe Y is emitting beta minus, then what will happen? It becomes Z by emitting beta minus means the Geiger-Müller count tube what you keep above the sample will count both alpha and beta. So the count rate will be more than activity of X or activity of Y. So there we can say the count rate is equal to sum, addition of the activity of X and activity of Y, but little bit confusing that time. But in your syllabus normally we consider the count rate is same as activity, and we normally consider a situation where the daughter nucleus is more stable. So if the daughter nucleus is very stable compared to X, yes, activity and the count rate will be the same. Otherwise, activity of X plus activity of Y will give the total count rate of the sample when we use Geiger-Müller tube. Okay, so activity means rate of disintegration. Rate of disintegration means now we'll go to the mathematical part or mathematical model related to activity. So rate of disintegration means, say for example, if there are n number of radioactive nuclei, what happens to the n? N will gradually decrease. So when the the element is X, the radioactive element is X, it consists of n number of radioactive nuclei at time t equals 0. That means we consider a particular time now, at certain time we take it as t equals 0. At that instant there are n number of radioactive X nuclei are there. So when it disintegrates, when X decays, the number of X will decrease. By emitting alpha or beta, whatever it is, the number of X will decrease. So rate of disintegration means rate of change of n. Rate of change of n. So rate of change, we learned that in mathematics. For example, if y is a fx is a function, rate of change we say dfx over dx. That's a mathematical format we approach rate of change. So the rate of disintegration of the number of radioactive nuclei present is dn over dt in terms of time. But we know n is decreasing. It's a decreasing function. It's a decreasing function. So if I say draw a graph n against time, it's a decreasing function. It's exponentially decreased, but I don't want to show an exponential decay. Something is decreasing. So if it is decreasing, the tangent will have a negative value. That's a dn over dt. So the rate of disintegration is a negative quantity. That is called activity. That is called activity. So A means activity is the notation for activity is A, that is minus dn over dt. Why we use minus sign? Because n is a decreasing function. That means the number of radioactive nuclei will decrease with time. That's the reason we have a negative sign here. The reason, anything decreasing function, if you draw a tangent, that's a differential, the meaning of the differentiation. So that's a tangent that will have a negative value. Okay, when we talk about radioactivity, we say two different properties regarding radioactivity. Radioactive decay, we say two different properties. One, we say it's a spontaneous emission. I already told that in unit 1, the first lesson also. Spontaneous means it happens in its own without any external interference. The second one we say is a random process. So what do you mean by random means in term of in term of timing, the individual decay of nucleus is random. That means we can't predict which nucleus will decay at an instant. So when we consider each and every nucleus, radioactive nucleus in the given sample, it looks random. We can't specifically tell at which time this nucleus will decay, when will this decay, we can't specifically tell. It looks random in terms of individual nucleus. But when we consider large number of radioactive nuclei, large numbers means several millions of radioactive nuclei, they follow a pattern. So statistics, we can use a statistics, just not for 1, 2, 3 radioactive nuclei. When there are a lot of radioactive nuclei, large number of radioactive nuclei, the way they disintegrate follows a pattern, a mathematical model, or we can say it follows statistics when there are a lot of radioactive nuclei. So what's the most suitable mathematical pattern is the rate of disintegration dN over dt is directly proportional to the number of nuclei, number of radioactive nuclei remaining there. Say if there are n number of x radioactive elements at that instant, the rate of disintegration, that should have a minus sign, I already explained that, the rate of disintegration is directly proportional to the number of radioactive nuclei remaining in the sample. That's the most suitable mathematical model where we consider larger number of radioactive nuclei, not for 10 or 20. Okay, so you know the statistics becomes more accurate when there are a larger number of data. So here the data means larger number of radioactive nuclei. So minus dN over dt is directly proportional to N. We know that when we convert a proportionality into an equation, there will be a minus constant. So minus dN over dt equal to lambda N. So lambda is called decay constant. Experimentally they found that is constant for a particular type of radioactive sample. If it is like a radioactive element, not a sample, radioactive element. Say for a radium, yes, lambda has a specific value. But when you think about another radioactive alpha, say for example, when it comes to the alpha particle, when you comes about thorium, yes, the value of lambda will be different, but that is constant for thorium. Regardless of the number of thorium nuclei remaining, lambda is constant. Okay, so lambda is called decay constant, and it is constant for a particular type of element. And also lambda is less than 1. We know that because otherwise it can't be equal to 1. If it is equal to 1, at an instant all the n will decay. So always lambda is less than 1. So we say lambda indicates the probability of decay. Lambda indicates the probability of decay. Okay, so we know that dN over dt is denoted by A, activity. So minus A equal lambda n, or A equal minus lambda n. But when we do numerical calculations, we don't consider the minus sign. So this is the first equation we are going to use, A equal lambda n. So here the unit of A is per second. So per second means there's a SI unit called becquerel, BQ, denoted by BQ. So A indicates the rate of disintegration activity. Its base unit is per second. SI unit is becquerel, denoted by BQ. Okay, so we got the first equation related to radioactive decay. So we are going to proceed further. That means we know that dN over dt is equal to minus lambda n. Okay, so we are going to get a relationship between the number of nuclei remaining in the sample. Okay, I told at an instant if there are n not number of nuclei, what will be the number of nuclei later at time t? We can get it from this mathematical model. So we know that dN over dt equal minus lambda n. we'll integrate it. dn over n is equal to minus lambda dt. So we can integrate. Now mathematics, we'll integrate it, not in the syllabus, but just I am doing it. Some students like to know that. So imagine initially at time t equals 0, there are n naught number of radioactive nuclei. Later at time t, so the number of nuclei present at time t equals 0 is n naught. So at time t equals 0, the number of nuclei remaining in the sample is n naught. Later at time t, the number of nuclei remaining is n. Okay, so integrated, you know 1 over n dn is ln, the natural logarithm, ln n. So that's going to be n naught to n. This is minus lambda t 0 to t. Okay, so we know that ln n minus n naught, so we can say ln n minus ln n naught is equal to minus lambda t. That is ln n over n naught equal minus lambda t. So take antilog on both sides. N over n naught equal e to the power minus lambda t. N equal n naught e to the power minus lambda t. Very important equation in your syllabus that relates when t equals 0. When substitute t equals 0, you'll get e to the power 0 is 1. So t equals 0, the number of radioactive nuclei present in the sample is n naught. Later at time t, the number of nuclei remaining is n, which is less than n naught. So the second equation, n equal n naught e to the power minus lambda t. Okay, so both sides of this equation could be multiplied by lambda. So I told for a given type of sample, lambda is constant. Both sides multiplied by lambda. So lambda n equal lambda n naught e to the power minus lambda t. So lambda n is A. Lambda n is A, activity at time t. Lambda times n naught. Lambda times n naught. N naught is the number of radioactive nuclei present in the sample when t equals 0. So lambda n naught is the initial activity, A naught e to the power minus lambda t. So the third equation, A equal A naught e to the power minus lambda t. Not only activity, even mass of the radioactive element in the sample, mass of the radioactive element in the sample, because number of radioactive nuclei in the sample decreases exponentially, means mass of one nucleus has no change. So mass of the radioactive element or mass of the radioactive element in the sample also will decrease exponentially. So we can use m equal m naught e to the power minus lambda t for the mass of the radioactive element present in the sample. Not only that, I told that if the daughter nucleus is stable, then the count rate also will decrease exponentially, because I told count rate will be same as the activity. So the count rate also will decrease exponentially. Okay, so all these equations are valid only when there are larger number of radioactive nuclei. Then the theoretical graph, you know, exponential graph in mathematics, you would have learned the shape of the exponential graph, and the practical graph will overlap. But if the number of radionuclei is very low, something like few hundreds, then the random nature of the individual nuclei, I told that already, radioactive decay is a random process. Individually, they are random process. So when the number of radioactive nuclei becomes very small, maybe around few hundreds, then the random nature of the radioactive nuclei, individual radioactive nuclei will become dominant, and they will not follow the activity, or the count rate will not follow this mathematical model. So there the random nature will become dominant. So this is true when there are larger number of, practically this is true, this we got through mathematical model, but it will tally with the practical model when there are larger number of radioactive nuclei present in the sample. Okay, so we can plot or we can sketch graphs related to these equations. So n equal n naught e to the power minus lambda t, you know the shape is an exponential decay, so exponential graph. So the y-axis n and x-axis time means the graph will be this shape. It won't touch the x-axis theoretically. When t equals 0, the number of nuclei remaining is n naught. The same way when we plot sketch a graph of activity against time, the graph will be the same shape. It will take exponential decay. It won't touch the x-axis. So here 0, this will be A naught. A naught is the activity when t equals 0. Okay, also you should be able to take the linear format of this graph. How to convert an exponential graph or exponential function into linear function? By taking natural logarithm, by operating by natural logarithm on both sides. So n equal n naught e to the power minus lambda t. So take both sides ln n equal ln n naught plus ln e to the power minus lambda t. So that will become ln n minus lambda t. Ln e is 1, so minus lambda t. So here also we can sketch a graph. Y-axis ln n. This is a constant, so we'll keep it as gradient plus ln n naught, sorry, ln n naught. So this could be on the y-axis. Minus lambda is the gradient, t is the x-axis, and this is the y-intercept point. So if you plot a graph or sketch a graph, ln n against time is a y equal minus mx plus c format. So the graph will be this shape, a straight line like this. So here this is ln n naught. The gradient of the graph will give minus lambda. Same way we can plot graph for ln A. Take this one, ln A against time, the same shape. There will be, gradient will become minus lambda. Okay, so next thing is half-life. Half-life means, at a particular instant, the activity or the number of radionuclei present has a value n naught. We call it as initially. Even something like same thing what we take in mechanics unit 1. Initially means at a time t equals 0 mathematically. So initially t equals 0, the number of radionuclei present in the sample is n naught, or at that moment initially the activity is a naught. So say for example, maybe the activity, imagine activity and count rate are the same, is actually maybe 200 VQ. How long will it take for this 200 VQ to become 100 VQ? Then how long will it take this 100 VQ to become 50 VQ? Will it be the same, the time interval for 200 to become 100 and 100 to become 50, will it be the same? Or maybe from 80 VQ to drop to 40 VQ, will it be the same as this time? Here, same is it? Same way, this, so will it be the same? We will see mathematically, right? So even though we say that it's a random process, it obeys the radioactive decay obeys this mathematical model when there are larger number of radioactive nuclei. We'll see is it possible for the time to become half of the previous quantity, such as activity to become half or the number of radioactive nuclei to become half for any value. Will it be the same? We'll see. Okay, so n equal n naught e to the power minus lambda t. That time, the average time taken for the activity or the number of radioactive nuclei remaining in the sample to become half is called half-life. and we denote it by T half. This is the notation, T half. Half is the subscription, it's a notation. Average time taken for the activity or the number of radioactive nuclei remaining in the sample to become half of the previous value is called half-life. We are going to check whether it is a unique value for a given type of sample. We'll see mathematically. Okay, so n equal naught e to the power minus lambda t. So t half is the time taken for n naught to become n naught by 2, is it? So n naught by 2. So n naught to become n naught by 2. What's the meaning of this equation? You should understand the meaning of this equation. You should be able to interpret this equation. The meaning of this equation is when t equals 0, the number of radioactive nuclei present in the sample is n naught. Later, at time t, the number of nuclei present in the sample is n. So now what I am taking is, when t equals 0, initially the number of nuclei present in the sample is n naught, arbitrary value n naught. So how long will it take t to become n naught? We'll see that. So n naught by 2 is equal to n naught e to the power minus lambda t half. We'll get an expression for n t half. And we'll see, will it be a constant? Yes, n naught and n naught will get cancelled. So half equal e to the power minus lambda t half. This I can write half equal 1 over e to the power lambda t half cross multiply e to the power lambda t half equal to, take both side ln. When you take ln of e is equal to lambda t half equal ln 2. Make the t half subject. So t half is equal to ln 2 over lambda. ln 2 is 0.609 or something like that, but ln 2 over lambda. Now you can see that this equation is independent of the number of nuclei remaining in the sample. That means whether 100 to become 50, but this number is very low. I told you this is true when there are larger number of nuclei, but I am just taking for you to understand the relationship. 100 to become 50, or 800 to become 400, or 2000 to become 1000, or 4 million nuclei to become 2 million nuclei, or whatever the value, the time is constant, because I told that ln2 is a number, lambda is constant for a particular type of sample. Say for example radium, lambda is fixed. So the time taken for 100 to become 50, or 800 to become 400, or 2000 to become 1000, or 4 million to become 2 million, or 100 million to become 50 million, the time is the same regardless of the number of nuclei present in the sample. To become half, that is same. How is it possible? Because even when it shows random nature for individual nuclei's decay, but when there are collective decay, when we consider several thousands or several millions of radioactive nuclei together, it becomes a mathematical model where in which the decay, the time taken to become half is constant. So this is not a good example, 100 to become 50. Certainly there will be random nature will become significant. Even this is not a good one. This is also not good one. I just took that those example for you to understand. It should be, say something like 20 into 10 to the power 10 to become 10 into 10 to the power 10, half of it. Or 12 into 10 to the power 12, or 10 to the power 10 to become 6 into 10 to the power 10, or 8 into 10 to the power 11 to become 4 into 10 to the power 11. So I should use and show larger number of nuclei. Then only the mathematical model and the practical will become the same. Because the statistics is true when there are a larger number of radioactive nuclei. So that is called half-life. During radioactive decay, energy will be released. First, we'll consider what's the energy released during alpha decay. During alpha decay, the energy release will be the kinetic energy of both the kinetic energy of the alpha particle and the daughter nucleus. The daughter nucleus will have a recoil velocity, so it will have kinetic energy. Okay, so what's the reason for energy release during alpha decay? During alpha decay, energy is released due to two reasons. First one is there will be mass deficit. So during alpha decay, when you add the mass of the daughter nucleus and mass of the alpha particle, that total mass will be lower than mass of the parent nucleus. So there will be a mass deficit or mass defect. So according to special theory of relativity, mass has equivalent energy. So this missing mass, that means in small classes like general science or even classical physics, we learn that mass is conserved. But here mass is not conserved. What happened? The missing mass is converted into kinetic energy of both alpha particle and the daughter nucleus. So that is one of the reasons for release of energy. There is another reason. After throwing away two protons and two neutrons from the parent nucleus in the form of alpha particle, the remaining nucleons form the daughter nucleus. So the remaining nucleons will try to get the lower nuclear potential energy. There will be change in the configuration of the energy arrangement of the nucleons inside the nucleus. So they'll tend to, or they'll try to get the lowest possible nuclear potential energy. So therefore the total potential energy of the, anyway not in the syllabus, but anyway I'll tell you, the total nuclear potential energy of the daughter nucleus will be lower than the total nuclear potential energy of the parent nucleus. So there will be energy release due to change in configuration of the nucleons, the arrangement inside the nucleus in terms of energy levels. So these are the two reasons for release of energy. First one is mass deficit or mass defect. The second way is the change in configuration of the nucleons inside the nucleus. But the energy released due to mass deficit is the dominant, or that has the most impact in the total energy release. So if you want to find the energy release in during the alpha decay, we mainly consider the amount of mass deficit, and we use the E equal mc square. We don't need to consider much about the change in the nuclear potential energy due to the rearrangement of the nucleons, because that gives very small amount of energy release during the alpha decay. So we don't consider much. So we need to consider only the mass deficit. So we find the mass deficit, delta M is equal to mass of the parent nucleus minus mass of the daughter nucleus and mass of the alpha. So that will give the mass deficit. We have to convert it in kilograms. Then energy released equal delta M times C square. So this will be the energy release during alpha decay, because mass deficit is the dominant in the amount of energy release. The change in configuration of the nucleons inside the nucleus, that also release energy, but that is not significant, because during alpha decay reasonably larger change in mass happens, because two protons and two neutrons are thrown away from the nucleus, or four nucleons are thrown away from the nucleus, causes significant change in the mass. We find the energy release by using this method. Okay, there's another method that also related to this one. The second method we can find in terms of binding energy also. That is true for alpha decay. The amount of energy release, that I use capital E, the energy release is equal to, the total binding energy of Y and alpha, the total binding energy of the daughter nucleus and the total binding energy of the alpha particle and the binding energy of the Y nucleus. When you sum, that will become more than the binding energy of the parent nucleus. When you check, when I give you next time, I'm going to do the numerical calculation, there you can see binding energy per nucleon of Y is more than the binding energy per nucleon of the parent nucleus, because binding energy per nucleon, I told that in the first lesson, binding energy per nucleon indicates a stability. The binding energy per nucleon of the daughter nucleus will be more than the binding energy per nucleon of the parent nucleus. But here we consider the total binding energy or sum of the binding energy of the daughter nucleus and the alpha particle. That will be more than the binding energy of the parent nucleus. The difference gives the energy release. So they can ask in terms of binding energy also. This is one method to find the energy release during alpha decay. The second method is binding energy method. So energy release E is equal to binding energy P dot E dot binding energy of Y plus binding energy of alpha minus binding energy of X. This way also we can find it. So I told the two reasons for energy release is mass deficit one. The second reason is change in configuration of the nucleons, but the effect due to change in configuration of the nucleons is not significant. So we find the energy release in terms of mass deficit E equal delta MC squared. The second method is energy release is equal to difference of the binding energy, sum of the binding energies of the daughter nucleus and alpha particle minus binding energy of the parent nucleus. That gives the energy release during alpha decay. Now I'll do a worked example. Okay, before doing the example, I want to tell you one more thing. How to find the kinetic energy of the alpha particle. So what we calculated there, the mass deficit method or binding energy, the difference of the binding energy method gives the total energy released. So total energy means that's the kinetic energy of the alpha particle and the kinetic energy of the daughter nucleus. How to find the kinetic energy of the alpha particle? What ratio they will get out of the energy release? Okay, we can find it like this. Okay, the idea, before the parent nucleus decays, it is at rest. So here I told that it's at rest means its momentum is zero before emitting alpha particle. In my first lesson, I told that during all type of nuclear decay, momentum is conserved. So momentum is conserved, therefore initial momentum equal to zero, momentum of X is equal to zero, because X, the parent nucleus, is initially at rest. We know the notation for momentum P, Px is equal to zero. So that means momentum equal to zero means momentum of Y plus momentum of alpha. That means momentum of Y is equal to minus momentum of alpha, means both will have the same magnitude of momentum but in opposite direction. So minus sign indicates they are in opposite direction. Let it be P. So Py equal P alpha, numerically minus sign indicates they are in opposite direction. So I generally put the momentum of Y or momentum of alpha is equal to P. Okay, so the total energy release is E. As I told earlier, as I described earlier or explained earlier, it could be found by using mass deficit method or binding energy method. Anyway, the energy release is E, that is equal to kinetic energy of the daughter nucleus plus kinetic energy of the alpha particle. We learned that in unit 4, kinetic energy is equal to P squared over 2m. We learned that in unit 4 momentum and also given in the data sheet, equation sheet. So this one I can write kinetic energy of Y means P squared, because momentum of Y is equal to P squared over 2 times mass of Y plus P squared 2 times mass of alpha. Okay, so we can find the ratio of kinetic energy of alpha to kinetic energy of the daughter nucleus. Kinetic energy of alpha is p squared over 2 times mass of alpha, p squared over 2 times mass of alpha into 2 times mass of y over p square. Simple relationship we are getting. I hope you understood. Kinetic energy of alpha to kinetic energy of y. P squared over 2 times mass of alpha is the kinetic energy of alpha. We are dividing, so into the other way, it comes the reciprocal. 2 times mass of y over p square. P square will get cancelled, 2 will get cancelled. So now we can come to the final relationship, that is kinetic energy of alpha to kinetic energy of daughter nucleus is going to be mass of the daughter nucleus to mass of the alpha. Normally we know that during, I told that alpha decay happens for massive nuclei, such as I told the examples when I start this lesson there. I showed that mainly it's like something like for example, if I take polonium becomes Pb lead, or thorium becomes radium with emission of alpha. So whatever it is, say for example, when thorium decays into radium and alpha, radium mass is almost the mass number 224, alpha is 4. So if it is like a decay of thorium, when I consider mass of the decay of thorium, so decay of thorium, this decays, like example I am taking, it becomes radium and alpha 42. So this is 228, this is 224. So the mass numbers almost equal to mass. Yeah, slight difference could be there due to the binding energy. But anyway, 224 and 4 means mass of the daughter nucleus 224 over mass of alpha 4. You can see how many times it's greater. No? It's actually almost 5 point something, like 50 times it's greater. Understand? So that's the reason most of the energy released will be taken by the alpha particle, because the relationship, better remember, the kinetic energy of alpha to kinetic energy of the daughter nucleus is other way, mass of the daughter nucleus to mass of the alpha. Most of the alpha decays, the mass of the daughter nucleus is reasonably larger compared to mass of the alpha. So most of the energy release will be taken or absorbed by the alpha particle. Okay, so this is the given example. Polonium isotope 210 mass number decays into lead 216 and alpha. So here the masses of polonium nucleus in terms of unified atomic mass unit given lead and mass of alpha. So we will find the mass deficit. So here I answered it. The mass deficit we are going to find it. Delta M is equal to mass of the polonium minus mass of lead plus mass of alpha. So that is mass of polonium 209.98 286 minus mass of lead 205.97 446 53 plus mass of alpha 4.00 260. So that is in terms of unified atomic mass unit. So we will get 5.7947 10 to the power minus 3 unified atomic mass unit. 1 U is equal to 1.66 10 to the power minus 27, convert to kilogram. 5.7947 10 to the power minus 3 into 1.66 10 to the power minus 27 kilogram. So that will become 9.619 10 to the power minus 30 kilogram. So energy release is equal to delta M mass deficit into C square. So 9.619 10 to the power minus 30 into 3 into 10 to the power 8 all things squared joules. So there you will get it, uh, yeah, 8.657 10 to the power minus 13 joules. So that's the energy released totally as sum of the kinetic energy of alpha and the daughter nucleus. Together the total energy release is this amount. This is first method in terms of mass deficit. What we can find if we are given binding energy. So here what is given? The given data is mass of the polonium, mass of the Pb and the mass of the alpha nucleus. Masses are given, but they can give the binding energy of each of these nuclei also like this. So there if the given data is binding energy of polonium, if it is given like this 2.56985 10 to the power minus 10 joules binding energy of Pb, this lead nucleus, 2.53476 10 to the power minus 10 joules. Then binding energy of alpha, you know alpha is a helium nucleus, it also has binding energy of alpha, that will be 4.3749 10 to the power minus 12 joules. Okay, so in this one, method 2, earlier I found it by using mass deficit. If the binding energies are given, there we can find the energy release as binding energy of the sum of the binding energy of the products, that is Pb and alpha, minus binding energy of the polonium. So binding energy of Pb plus binding energy of alpha minus, I will erase it, so remember the answer 8.657 10 to the minus 13 minus binding energy of polonium. Okay, substitute the values. Binding energy of Pb, that is 2 point, you substitute the values, yeah, you'll get the answer. Substitute binding energy of Pb. Binding energy of Pb is given 2.534 into 10 to the power minus 10. Binding energy of alpha 4.3749 10 to the power minus 12 minus binding energy of polonium 2.5698 10 to the power minus 10. Solve it. You will get almost the same answer, 8.659 10 to the power minus 13 joules, same as earlier. Okay, you can see both methods give exactly the same answer. Okay, so the next topic is carbon dating. Carbon dating is one of the applications of radioactive decay. So you know carbon 14 is formed in the atmosphere. Carbon 14 has almost the same chemical behavior as carbon 12. So normally the amount of carbon 14 exists in the atmosphere remains constant. So during photosynthesis process, plants consume carbon 12 as well as carbon 14 also will be consumed by the plants. The amount of carbon 14 consumed by the plants depends on the amount of carbon 14 exists in the atmosphere. So, in the food chain, plants is at the highest position. So, from the plants, the carbon 14 will be consumed by all other living organisms. So, in our body also there is carbon 14. So, when we live, the amount of carbon 14 to carbon 12 ratio. So, rather than telling amount of carbon 14 in the body remains constant, I don't want to say like that. The ratio of carbon 14 to carbon 12 or the amount of carbon 14 to the amount of carbon 12, that ratio will remain almost constant during our lifetime. So when any living organism dies, it won't be able to consume further. So what happens? The carbon 12 is a stable nucleus, but carbon 14 is an unstable nucleus. So the carbon 14 will decay. So only the carbon 14 will decay, so the carbon 12 will remain constant. So the ratio of carbon 14 to carbon 12. So I can say the number of carbon 14 to number of carbon 12 in the sample will start to decrease. Okay, so if you find an organic compound in an archaeological site, there we can measure the activity, but sometimes measuring the activity might be difficult. So normally what they do by using chemical methods, they find the ratio of carbon 14 to carbon 12 in the sample. So if you find the ratio of carbon 14 to carbon 12 in the sample, you know that ratio, let it be R. We know carbon 14 has very long half-life, almost it's 11,500 years or something like that. It's a very big, 5,730 half-life of carbon 14 is almost 5,730 years. So reasonably during a shorter period the amount of decay is negligible. But when you find the ratio of carbon 14 to carbon 12 in the sample that found in the archaeological site, what should we do? We should find similar type of sample currently living, in which the currently living sample, similar type, if it is animal, plant, then the plant. So similar type of living organism in which we should find the ratio of carbon 14 to carbon 12, right? Then we assume when the sample found in the archaeological site, when it was living several thousand years ago, also had the same ratio of carbon 14 to carbon 12 like what we find in the currently living organism. But it might be wrong assumption, because in the past the ratio of carbon 14 to carbon 12 in the atmosphere could be different. But we assume we need to just at least find some value for the age of the sample. So what we do, similar type of current living organism in which we find the ratio of carbon 14 to carbon 12. Chemical method we use and we can find the ratio of carbon 14 to carbon 12 in that sample. Then we assume the sample what found in the archaeological site also had the same ratio of carbon 14 to carbon 12 as currently living similar type of sample, and we take that as R0, the ratio. So we know the relationship between R and R0 because that is due to decay of carbon 14. Decay of carbon 14 depends on the decay constant of carbon 14, which is given by T half equal ln2 over lambda. So that is ln2 over T half of the carbon 14. Then we can use R equal R0 e to the power minus lambda T, where lambda is the decay constant of the half-life, and we can find the time taken for the ratio of carbon 14 to carbon 12 to drop from this value to this value. this value to this value. So there we call it as age of the sample, but even though we call it as age of the sample, actually what we are finding, how many years ago the organic sample died. We can't say how many years it lived, we can't say, but we can say how many years ago the organic sample found in the archaeological site died. That's only we can find it. So that is called age of the sample. This is called carbon dating. Okay, so next thing is about the power emitted during radioactive decay. So power emitted during radioactive decay means amount of energy released per second. Amount of energy released per second. So during each decay there will be energy release. We know how to find the energy release during alpha decay. I showed it, mass deficit method or binding energy method. But during beta minus decay or beta decay, we can't find it just by using mass deficit, because that won't be the same as the energy measured during practically during beta decay, because energy release due to both mass deficit and due to rearrangement of the nucleons gives the total energy. Anyway, if we say the total energy released during a decay, whether it's alpha or beta, is E, that's energy release during a decay is E, into number of decay per second. Number of decay per second. Of decay per second. What is it? Number of decay per second. How many decay happens per second? That is the activity. So the energy per decay, one decay, how much of energy release, into energy per decay is the power released during 1 second. That's energy release during 1 second. So whenever they ask to find the power release during radioactive decay, we can say power release is equal to energy per decay into activity. Number of decay per second is the activity. So how many equations have we learned so far? First equation we learned A equal lambda n, then n equal a naught e to the power minus lambda t, A equal a naught e to the power minus lambda t. Then even for mass of the radioactive element, m equal, we can take m naught e to the power minus lambda t. Even count rate when the daughter nucleus is stable, we can say c naught e to the power minus lambda t. Okay, for carbon 14 to carbon 12 ratio during the carbon dating, the ratio of carbon 14 to carbon 12, that also follows the same format. Then half-life, T half is equal to ln2 over lambda, constant for a given type of sample or given type of element. Then the power release is equal to energy per decay into activity. These are the equations you better know in A2 syllabus. Okay, so we'll do a few questions related to exams type. So this is the first question. So they asked to find the activity. So radioactive element contains this much of nucleus. So radioactive N is given, then lambda is given. So that's very easy question. So first part we can find A equal lambda N. So lambda we know that 1.28 10 to the power minus 5 into n is 6 into 10 to the power 10. So that will be equal to 7.68 10 to the power 5 b cube. When you are using this equation, lambda must be in per second. But when you are using n equal n naught e to the power minus lambda t, the unit of lambda and t should be the identical. Say lambda is, if it is per hour, time should be hour. If it is year, per year, it should be year, the similar type. But when you are using A equal lambda n, lambda must be in per second. So second part, uh, T half is equal to, is given in the data sheet, ln2 over lambda. So ln2 over lambda is given 1.28 10 to the power minus 5. So that will be 8 5.4 10 to the power 4 seconds. Okay, so this is the second question. An element means there's a radioactive element X becomes Y by emitting a particle. Initially, the radioactive element X contains 5 into 10 to the power 8 radioactive nuclei. Its half-life is given. Find its initial activity. So, initial activity means I should know the decay constant lambda. A equal lambda n. N should be the initial number of nuclei that is given here. Okay, so I need to find the lambda. So, we'll use the equation T half equal ln2 over lambda. So from that we'll find the lambda. ln2 over half-life is given as 40 seconds. So the lambda will become 0.0173 per second. Then A equal lambda. In 5 into 10 to the power 8 BQ. Solve it, you will get the answer. That will be 8.65 10 to the power 6. Okay, so second part, find the number of nuclei of X after 8 minutes. So I can use the equation n equal n naught e to the power minus lambda t. We know the initial number of nuclei 5 into 10 to the power 8 e to the power minus lambda. We found it 0.0173 time. So I told that this and the unit of lambda and t should be the similar type. So this is per second. So time is given 8 minutes. I should convert to second. So you will get the final answer 1.238 10 to the power 5 BQ. Okay, so this is the third question. So there it says they found a rock sample in the moon. So there they know that potassium decays into argon-40. Half-life of potassium is given as 1.3 10 to the power 9 years. So when they test the rock, they found it consists of 0.84 microgram of argon-40 and 0.10 microgram of potassium. So the idea here, whatever the argon found, so decay of potassium to argon. So we know that potassium decays into argon. So we don't need what type of decay. So whatever the mass of argon found there is created from the initially it was as potassium. So here they are saying in the rock sample they found 0.10 gram of potassium and 0.84 gram of argon-40. So whatever the argon 0.84 there was initially in the form of potassium. So we should know the initially when the rock was formed, the moon. So the amount of argon, the mass of potassium in it was initially 0.84 microgram plus 0.10 microgram, that is 0.94 microgram initially the amount of potassium. Now the mass of potassium has dropped to 0.10. Now it has dropped to 0.10. So this is the initial mass of potassium, we can see M naught for potassium. Now M is 0.10 microgram because potassium is decaying into argon. So that's the idea. Potassium initially it consists of 0.94 microgram. Whatever the argon we've measured here, that is created from the potassium. So the initial mass of potassium there was 0.94. Now it is 0.10 microgram. So we can use m equal m naught e to the power minus lambda t, but only thing we need to find the lambda from this half-life. So we'll use that idea to find the lambda first. So T half is equal to ln2 over lambda for potassium. So lambda is equal to ln2 over half-life. T half is 1.3 10 to the power 9 years. So there you will get the answer. Over 5.33 10 to the power minus 10 per year. Okay, so for potassium we can use m equal m naught e to the power minus lambda t. So m naught 0.94, m 0.10 e to the power minus lambda 5.33 10 to the power minus 10 into t. Okay, so solve it. So then I reciprocal it. It will become 0.10 equal 0.94 into 1 over e to the power 5.33 10 to the power minus 10 t. So you know how to solve it. E to the power 5.33 10 to the power minus 10 t equal to 0.94 over 0.10. Take both sides ln and solve it for t. Here we will get the answer in years because the lambda we substitute in per year. So if this is in per year, we will get the answer in year. Solve it, you will get the answer in years. That will be 2.11 10 to the power 8 years. Okay, so this question, radium-226 emits alpha particle and its half-life is given. Each alpha particle carries an energy of this much. So most of the energy is carried by the alpha particle. I already told because of mass of the radon is much higher than the mass of alpha. So 226 gram of radium consists of, that's a 1 mole, that's a molar mass. 1 mole consists of 6.02 10 to the power 23 nuclei. Calculate the mass of radium that would produce a power of 55 watts. So I gave an equation, power equal activity times energy per decay. Energy per decay is given. So because actually here what is given is kinetic energy of the alpha particles, that will be almost equal to energy released per decay because most of the energy will be carried by alpha particles. Energy of the daughter nucleus will be much weaker because its mass is much higher than the mass of the alpha. So I can take the energy of the alpha particle, which is given as 7.65 10 to the minus 13 joule, as the total energy release. Almost it's very close a value. So we know power is equal to energy of decay into activity. So power we want 55 watts, energy per decay 7.65. I gave this equation, 7.65 10 to the power minus 13 in activity. So we'll find the activity, how much is the required activity to have a power of 55 watts. So we'll get activity 7.189 10 to the power 30 BQ. Okay, so I know the activity. The idea A equal lambda, and lambda I can find from the half-life. I can find the N, how much of radioactive radium nuclei should be there to give this much of activity, then only I can get the power. So I'll find the number of nuclei. To find that, we need to find the lambda, T half equal to ln2 over lambda. Lambda equal ln2 over T half, half-life is 1620. So I need to convert that to years because I need to find the lambda. If I am using A equal lambda n, A is activity, should be in becquerel, means per second. So I need to convert the years to seconds. So 1020 years to convert to second, 365 days, 24 hours, 60 minutes, 60 seconds. Is it? Per second. So the lambda will be 1.36 10 to the power minus 11 per second. So I found the lambda. Then I can use A equal lambda, and I can find how many number of nuclei we need to have this activity. So 7.189 10 to the power 13 equal lambda. I found it 1.36 10 to the power minus 11 into n. Find the number of nuclei required to have this activity. So n will be 5.29 10 to the power 24. Okay, so 6.02 10 to the power 23 nuclei has this mass. How much is the mass of this number of nuclei? So mass of this much of nuclei, we need to find it. So because this much of nuclei required to have this activity required to have this power. So we need to find the mass. So that means 226 grams divided by 6.02 10 to the power 23 into 5.29 10 to the power 24. So that much of gram. So we'll get it 1,986 gram. That is almost 1.986, so almost 2 kilograms of radium we need to get power of 55 watts. Okay, so this is the fifth question related to carbon dating. When examining an organic sample in an archaeological site, might be a bone or whatever it is, archaeological site, scientists found that 2.3 10 to the power minus 11% of the carbon was C14. So that means carbon 14 to carbon 12, that percentage is this much. But in the recent same type of sample, so sometime you might not be able to check the amount of carbon 14 to carbon 12 in currently living organisms. So maybe you might check recent sample, maybe few days back or few years days before it died. So in which the ratio is 1.0 to 10 to the power minus 10. So you know half-life of the carbon 14 is very long, that is 5,730 years. Means if you take a sample that died around 10 days back or 1 year before, the ratio of carbon 14 to carbon 12 will be exactly or very closer to the currently living organism. So normally we should check it with currently living organism, but someday we won't be able to check it. So we can check the carbon 14 to carbon 12 recently died sample. So that is 1 into 10 to the minus 10 percentage. Okay, so find the age of the sample. So we know the initial, so we assume when the sample found in the archaeological site, when it was living, the ratio of carbon 14 to carbon 12, the percentage is this much. Now this much. So that's the way we have to take it when we are doing the carbon dating. Only thing we need to find the decay constant by using this one. So T half is equal to ln2 over lambda used for carbon 14. So decay constant we need to find ln2 over 5730 years. We'll get it in per year. So we'll get lambda, that will be 1.21 10 to the power minus 4 per year. Okay, so this is the ratio or percentage, whatever we can say, we'll say percentage. So ratio decreases exponentially, carbon 14 to carbon 12 ratio means the percentage also will decrease exponentially. So either way I can say ratio or percentage decreases exponentially due to the exponential decay of carbon 14 in the sample. Carbon 12 is a stable, so it won't decay. So now this percentage currently, when we check for the sample found in the archaeological site, 2.3 10 to the power minus 11. We assume when it was living, it had same as recent sample, that is 1.0 10 to the power minus 10 into e to the power minus 1.21 10 to the power minus 4t. We need to find the t, how long it took for this percentage to drop to this one, that we call age of the sample. Age of the sample means how many years before it died. That's the thing we are going to find it. So we know how to solve it. That is 1 over minus, so we can say e to the power 1.21 10 to the power minus 4 t equal to 1.0 10 to the power minus 10 over 2.3 10 to the power minus 3. It's maths, not physics. Now solve it. Take both side ln and find the t. You know how to find the t. Take both side ln. You will get 12,146 years. So that's the age of the sample. That means for 12,146 years ago, the sample found in the archaeological site died. Okay, so that's the end of second lesson in nuclear decay. In my third lesson, I'll discuss artificial transmutation. That means mainly fission, fusion, and few other examples related to other type of artificial transmutation. That means questions. There were questions in the past papers, Edexcel, IAL, bombarding a particular nucleus with alpha or bombarding a nucleus with proton. So that type of questions and theory I will do in my third lesson. This is the second lesson. So before watching this second lesson, better to go through the first lesson where I discuss about mainly binding energy and the conditions for stability of a nucleus. Okay, so I hope you understood. I'll discuss the third lesson very soon.